Hello, I'm glad to see so many people here today. Welcome to the third lecture in the LIR Berkeley in Space series. In our previous installments, we heard from a mechanical engineer, Panos Papadopoulos, about the challenges and prospects of sending humans far from the Earth into a hostile environment, and from an astronomer, Josh Bloom, about how AI offers the possibility of breakthroughs in problems that had not previously yielded to scientific efforts or only with great deal of time and effort. Our third speaker is an astrophysicist, Associate Professor Raffaella Margutti, who holds the Mark and Christina Bensadoun Chair in Physics. Professor Margutti was educated at the Università di Milano Bicocca, where she earned an undergraduate degree in astrophysics, and in 2010, her PhD in physics and astronomy. In her research, she specializes in violent, short-lived events such as stellar eruptions, stellar explosions, mergers of neutron stars and black holes, and she is a leader in a new field known as multi-messenger astrophysics with gravitational waves. Her studies rely on combining observations from across the entire electromagnetic spectrum with data from other phenomena, such as gravitational waves. She has been honored for her work in this field by being named a Sloan Fellow in Physics in 2019 and a Canadian Institute for Advanced Research Global Scholar in Gravity and the Extreme Universe in 2019. In 2022, she received the New Horizons in Physics Prize for her leadership in laying foundations for electromagnetic observations of sources of gravitational waves, and for her leadership in extracting rich information from the first observed collision of two neutron stars. So I'm delighted to welcome her here today to speak to us on the Renaissance of Astrophysics. Welcome, Raffaella.
Thank you so much for a very nice introduction. Yeah, and thank you all for tuning in. I hope I will be 1 hour of fun. And what I want to tell you today is exactly that story that led to the first and only detection of light coming from a place where we detected also gravitational waves. So I called it the Renaissance of Astrophysics, not because before we were dead, not at all, but because I believe that what is happening right now in astrophysics is very similar to what enabled Renaissance in my beloved country. So in Italy, Renaissance was mostly enabled by the fact that barriers between disciplines were torn down. And that is exactly what is happening right now in astrophysics. We are living through a very, very special time. It's a time where we can combine information coming from photons, coming from gravitational waves. So we have really to put together all of our strengths coming from different disciplines to understand our universe. So today, I want to tell you a little bit the story of what happened in 2017 and how that day, August 17, 2017, really changed the way we go about learning about our universe. So I'm going to first try to set the stage and try to make you understand and appreciate where the knowledge was before and what has changed. So as always, in research, we are dealing with large knowledge gaps. That is what I call ignorance, but it's a good ignorance. It's what really fuels our research. So we do know very well that we have stars and that sometimes the stars, they do explode. But what we really do not know is what they leave behind. Do they leave behind neutron stars? Do they leave behind black holes? We actually do not know, and we can't predict from first principles. What we do know for a fact and very well is that massive stars that explode, those are stars that are, let's say, 10 times the size of our sun. Those massive stars like to hang out in binaries. And sometimes, as we will see, they're capable of staying together until the very end. So you have a first massive star that explodes. Let's assume it produces a neutron star. And then the second one will also explode, it produces a neutron star. And sometimes this system is able to survive this very, very dramatic path, and together they stay together for a long time. As we learn, they can't stay there forever, and they merge. This is what we call neutron star merger. This is the moment where we do produce a lot of detectable now gravitational waves and also some type of light that is very special. So what I'm trying to explain, the questions that I'm trying to attack with my team here at Berkeley are as follows. I would like to understand exactly the physics of the merger, so what happens there. And I would like to understand what type of light is produced by this merger. And you will understand very, very soon why these are fundamental questions. So we do have a huge gap of our knowledge, but the message I want to convey today is that we do have the possibility to fill up this gap, not only with photons. Here I put photons across the spectrum, from the radio waves all the way to the gamma rays. But right now, we have the possibility to sample our universe using neutrinos and gravitational waves. So the story starts as follows. So this is an artistic rendering. So you will see something that is actually not how we observe the universe, but it is going to give you an idea. The story, so the rendering is fake, but the story is very, very, very true. So here you go. So 130 million years ago, in a galaxy that has that name, NGC 4933, there were two neutron stars, and those two neutron stars merged. And merging, we will see, produce a lot of particular type of light. And we will learn that there is that fluffy stuff and a jet. And today I want to tell you the story of this very, very special event. But to really appreciate what happened there and to understand why that matters at all, we need a little bit of context. So first of all, we know that for our recipe, we need two neutron stars. So I want to talk about a merger. So I need two of these neutron stars that can merge together. So let's start from scratch. How do we form one neutron star? Easy. We can answer to that question very precisely. We do know for a fact that what produce neutron stars are explosions of massive stars. And the reason why I can be here and tell you that this is absolutely true and correct is because we can use the observations in our own galaxy. So at the end of this movie, you will soon recognize a very, very famous nebula. So I'm sure that a lot of you have recognized here the Crab Nebula. So in the center of this Crab Nebula, which was the explosion of a star 1,000 years ago, at the center of that nebula, I don't think you can see my cursor, probably not, but you can see that tiny dot, white dot that is in the center of the nebula. That is a neutron star. You can clearly see it shining bright in the gamma rays. So if you look at the lower panel, you have the light emitted by this nebula from the radio all the way to the gamma rays. And you can see that in the gamma rays, I only have one source. That source is a neutron star. And then you can see how the same explosion, what is left behind effectively after 1,000 years, appears very, very, very differently depending what light we actually collect. But here, the most important message is that we do know that some type of explosions produce neutron stars. As I said at the beginning, I can't predict what type of star will explode and produce a neutron star, but I know that some do. So, and that was true. We knew that before 2017, we knew that to produce one neutron star, we need one stellar explosion. But hold on a minute, I need two neutron stars, right? Because I want to merge these two neutron stars. So how do we form two neutron stars? Well, easy. We start off with a system of two stars, so a binary stellar system. So we start off with the yellow and the orange star, and then the bigger star is the one that has more fuel to start with, but uses up much faster than the smaller star, so it will be the first one to explode. Well, the other one is right there, and hopefully is able to survive this very, very dramatic event. Let's assume that the first star, the orange one, has produced a first neutron star, and then we wait a little bit, and then the second star also undergoes a supernova explosion, and here is how we form a system with two neutron stars. But it's not as simple. First of all, we need to start off with a binary system of two stars that are massive enough to produce a neutron star. So to give you as a rule of thumb, to produce a neutron star, we need to be at the beginning of our lives at least 10 times the mass of the sun. So our own sun will not produce a neutron star. So, but let's assume that we have been lucky, and in our binary system, we got two big stars. Okay, great. This already limits the number of systems available. But not only that, we have two big stars, one explodes. As you might think, that explosion is very violent, and it's kind of tough for the companion to stay together. I mean, the companion has to stay tight to a star that has just entirely exploded. And it so happens that only a few percent of these binaries are able to survive the first explosion. And then, same thing later on, the second star will also explode. Well, just like before, it's not a given that the binary system can survive and stay bound together, but sometimes it does. So long story short, if you start off with your set of binary systems, only 1 out of 100,000 will actually be able to be together in the end. So the message that I want to convey is that those systems that we can detect now with gravitational waves that are the result of the merging of two neutron stars are rare. They are rare outcomes of stellar evolution. So it takes a lot to stay together, to be born with the right conditions, but also to stay together until the end. But in spite of being rare, they actually happen. And here is, I'm going to add another piece of information. So not only those systems are rare, but the second question that we want to try to understand is, okay, I formed two neutron stars. Why those two neutron stars could just stay there and rotate around each other forever? Why that is not possible? Why are we talking about mergers? And the reason has to do with the fact that that system of two neutron stars that are rotating around each other is a system that has a leak. It has a leak of energy, and that leak is due to energy that is taken away by gravitational waves. We did know very well, way before 2017, that gravitational waves were most likely the way that this system was, they were losing energy. And the reason why we did know has to do with observations from Hoff and Taylor, and they were awarded the Nobel Prize in 1993 for this. So if you look at the plot that you have on the left part of the screen, you have on the y-axis a measurement of how tight the orbit of these two neutron stars is. And the smaller, the more they shrink. And then on the x-axis, you have years, the calendar years. And then you can see the measurements, the little dots, and then you can see how this system was clearly shrinking. So the orbit was becoming tighter and tighter. And not only the system was shrinking, but then you can overlay on top of the data point a prediction of general relativity. So this is not a fit to the data. So I'm not trying to force my model to reproduce the data. I'm really just asking the general relativity, the Einstein general relativity, to tell me if it is true that this system is losing energy through gravitational waves, how would the orbit behave? And you can see this amazing, amazing agreement between the predictions of general relativity and what we were seeing. So the bottom line is that we did know that neutron star binaries could form, and we also knew very well that they could not stay there together until the end of times. But the system would try to become tighter and tighter, and the consequence of that is that at some point these systems would merge. Let me add another thread to this, so a little bit more context, which right now will look like it has nothing to do with what I told you until now. So since the 60s, a type of source known as gamma ray bursts were known to exist. So those were pulses of gamma rays, and so they were named gamma ray bursts. They were first discovered in the 60s, and that is not by accident. And the reason is that there were satellites, the Vela satellites, that were put on orbit, not really to study the universe, but with a different goal. And the goal was to try to monitor nuclear weapon experiments. And one of the way you can detect if somebody is trying out some nuclear weapon is by detecting the gamma rays. And that's why the Vela satellites were launched. And so they started detecting some bursts of gamma rays in the 60s. And for 10 years, until 1973, these gamma ray bursts remained military secret. The reason being that it took a while for people to realize that these gamma ray bursts had nothing to do with humans, thankfully, but they were actually produced by the universe. One of the key elements of observations that led to this conclusion is that these gamma ray bursts were very, very uniformly distributed across the entire sky. While if you think about somebody trying out some nuclear weapon, you would expect the gamma rays to come from some particular direction. So, basically, since the 70s, we knew that of the existence of this gamma ray burst. But one of the theories that was put forward was that these gamma ray bursts were actually related to the collision of neutron stars. And there was some evidence before 2017 that this theory had some hopes to be right. However, we were missing a smoking gun for this theory. So now let's stop and think, and let's try to put together everything I told you so far. So what I told you is that we do have the possibility in the universe to produce couples of neutron stars. Those are rare systems. However, they can't stay there forever. They are expected to merge. And when they merge, we do expect something very violent to happen, and maybe we also leading to the release of gamma rays. That's where we are. So let me add yet another thread here. This has to do with the origin of the heavy elements in the periodic table. And again, it seems that this is also completely unrelated from what I've told you until now, but then in the end, we will see how everything ties together. So you have a map of the periodic table, and I color-coded this periodic table depending on the origin of these elements. And here, I just want to emphasize and draw your attention to the orange ones. You can see the merging neutron stars. It seems that they start appearing in the lower part of the periodic table. So this seems to, we thought that they would be responsible for what we call the very heavy elements. And this right now is pretty much the accepted picture that merging neutron stars have a lot to do, for example, with the production of gold. I typically use gold because almost all of us can relate to that element, but they are responsible for production of a lot of the other heavy elements. But for example, when I was going in grad school, and that is, well, it's more than 15 years ago, but back then, this periodic table would have looked entirely different. So neutron star mergers would basically not even appear. And we would think that instead supernovae, so stellar explosions, could do it all. But today, I'll try to convince you that we actually have evidence right now, direct evidence that neutron stars do produce the heavy elements. So if you're wearing right now something that is made of gold, think about how amazing it is that that piece of gold at some point was forged in a neutron star merger, and then the elements slowly and slowly made all their way to planet Earth. I always find it very, very, very romantic. So, so here's what happens. So I told you about neutron stars, I told you about gamma ray bursts, I told you about heavy elements in the universe. And now the story is that all of these kind of different threads were all united in what happened on August 17, 2017. And the story of that event starts off in the gravitational wave part of the phase space. So what you see here, so you have a list of on the far left, you see a list of events they take the name of either GW or LVT. For now, just forget about GW, LVT, just focus on GW events. GW stands for gravitational wave event. And then the event takes the name of the year, month, and day when it happened. So the first ever gravitational wave detection happened in 2015, September 14th. So you have GW 150914. This is the very first time we detected, as humankind, we detected gravitational waves from our universe. It led to a Nobel Prize the following year, and what produced these gravitational waves was the merger not of a neutron star, but of a pair of black holes. And then you have a number of other black hole mergers, and the reason why we have those there will be very clear very soon. So let me play let me play here the video. So I'm playing the gravitational wave signal from 1708-17 in the bottom. That yellow line is basically what I'm referring to. And it doesn't take any gravitational wave expertise to understand immediately that the duration of the signal of gravitational waves around 1708-17 doesn't really look like anything we had seen so far. Just look at the black hole mergers above. They're really short signals. They end very quickly. And instead, after 45 seconds, we're still dealing with the little signal from the neutron star merger. And that noise, I hope you could hear it, is literally the noise of what that corresponds to the frequency of the gravitational waves, because the frequency of gravitational waves are actually, you can actually perceive that with our ears. So the bottom line is that we have black hole mergers that we were used to detect for 2 years at that point. And then in August 17, 2017, we have that very, 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 very long signal. And the fact that the signal was so long-lived was already telling us that that system that was merging was not a black hole system, but it was made of neutron stars. It all starts from here. So what you see in this diagram is a diagram of all the pairs of compact objects that were known at that point. And you have on the y-axis, you have a scale of mass in solar masses. So one is as masses of the sun, and you can go up all the way to 80 times the mass of the sun. And the diagram is such that it takes, basically you see we start off from two dots. So those are the compact objects before the merging, and then they become something else. They become a bigger one, a bigger black hole or something else when they merge. And the event that we're talking about is far down. We started off with objects that were 1 point something the mass of the sun. That's a typical mass of a neutron star. And then, as you can see, I'm not capable of telling you what did they produce. This is one of the big questions that were left pretty much unanswered. So we do know that we started off with 2 neutron stars, but we don't know what we formed, most likely a black hole. So let me tell you the story. In addition to science, I would also like to try to convey something about what happens in the day-to-day life of a multi-messenger scientist. And so I'm going to tell you the story from my own perspective, and I'm going to tell you the story basically from the very beginning. So it is August 17th, 2017, and I was living in Chicago. So for me, it's 6 a.m. Actually, okay, here I translated into Pacific time. So it was 9 a.m. It was 8 a.m. for me, but it was 6 a.m. here at Pacific. And then at that point, we receive a LIGO alert. What does it mean? What it means is the following, that there is the way we get to learn about a new neutron star merger or black hole merger is actually through our phones. There is an app, if you're interested, it's the LIGO app. If you can see my screen, I have it on my phone. And then when we have, when there is a detection of a new event, we get paged on the phone, and this tells us new event found here at this time. So please start working. That's how it works. So Pacific time is 6 a.m. We received the alert, so we received the text message. And we clearly realized, because of that very long duration of the gravitational wave signal that I showed you in the couple of slides before, that this is actually not a black hole merger, but this event has a neutron star. For anybody that is trying to find light coming from these dramatic mergers, having a neutron star is key. Why? Because there is matter. So to produce light, we need some sort of matter, and having a neutron star involved is what gives us the best options. So we understood immediately this was the event of my my entire career, that was waiting for my entire career. And so not only there is a gravitational wave signal, so on the bottom of this plot, you have a frequency versus time. This is how we look at the gravitational wave signals. And you can see at time starts from -10 seconds. In this case, we focus on the end, so right before the merger. And then you can see how, as time goes by, the frequency of the signal goes up, because it's sort of tied to the how fast the two neutron stars are rotating around each other. And then you can see at some point we merge down, we become something else, that question mark that I told you earlier. And not only we have a gravitational wave signal, but 2 seconds afterwards, both the Fermi satellite and Integral, both are gamma ray satellites, both of them independently record the presence of gamma rays, of a burst of gamma rays, 2 seconds delayed. So that's the merger time. This is the red line, and then there is this burst of gamma rays that happened, or at least got to us 2 seconds after the merger of the two neutron stars. But not only the event, the gravitational wave and the gamma rays were happening at the same time, but they were also coming from roughly the same location in the sky. So what you're looking at here is a map of the sky. And let me walk you through it here. So the gravitational wave detectors, they are not very good in telling me where in the sky the event happened. And for example, here you can clearly see that the LIGO interferometers, so those are the detectors that are based in the United States. Those told us that the region of interest was the light green one. And you can see there are those two bananas, one in the northern sky, one in the southern skies. So they were telling me it's somewhere there. Then, if you add the information coming from a third gravitational wave detector, Virgo, that is in Italy, then the region shrinks down to the darker part of the green of the two green bananas, and only one of the two is selected. So the addition of a third gravitational wave detector allows me to remove the degeneracy, and now I know that I don't have to pay attention to what happens down, but just to the green part that is above. And then we have the localization that is coming from the two gamma ray spacecraft. So you see the localization of the Fermi satellite, it's dark blue, and the localization of the light blue, which is the localization of another network, the IPN and Integral. The key point here is that if you overlap all of these localizations, they do share a common region, which is what is emphasized right there with the dark green circle. They all overlap there. So not only the gravitational waves and the gamma rays were coincident in time, roughly, but they were also coincident in space. And this, of course, increases the probability that those two events are physically related. So just to have an idea of how well this event was localized, so consider that the localization that was given to us, astrophysicists trying to find the light coming from this event, was of the order of 28 square degrees. And let me just try to quantify how bad this is. If you think about how big is full moon in the sky, this is actually of the order of tenths of full moons in the sky. This is just to say that the gravitational wave interferometers, they're very good in telling you when things happen, but not where things happen. So the challenge for us is to go into this vast regions of the sky and try to pinpoint the exact location of where that event happened. So this is exactly what we try to do. So again, it was 6 a.m. Pacific time, and we were trying to localize the event using an optical survey. And it so happened that the only place where we had access to telescopes would see the night 11 hours after the merger. Of course, in the optical, from the ground, you have to wait for the sun to set. So we had 11 hours. So we had to wait until the sun would go down. And you might think that we were just there waiting for that to happen, but actually those were the most hectic 11 hours of my life, probably. So during these 11 hours, what we were trying to do was to try to ask our gravitational wave astronomers to refine their localization. And then in parallel, we were re-optimizing our strategy to try to pave the region of the sky in the most intelligent way and trying to find the counterpart of this merger. And specifically, I'm going to tell you the story of the team I was part of that had access to DECAM. DECAM is a telescope that is in Chile. One of the key features of this telescope is that it has very wide eyes, so you can actually image large portion of the sky at the same time and then move to the next style. So you can actually pave the region, localization region of the gravitational waves very efficiently. So here is the team I was part of. Let's see our setup. So here is how we thought it would happen. So we have the alert coming from our gravitational wave detector. You can see those two very long arms, that L-shaped thing that you can see in the upper left part. That's a gravitational wave detector. So the way we envisioned this experiment to go was as follows. We received the alert. Once we get the alert, we're going to trigger, so we start observations on our wide field of view telescope. The PI of this effort, of the optical effort, was Ido Berger at Harvard. And then once this instrument is able to tell us precisely where the neutron star merger happened, we will repoint instruments that are more sensitive, but they have very small field of view. So they can go deep, but they need to go they need to know where to look. So we would then repoint spectroscopy, and this effort was led by Ryan Chornock. Ryan is now faculty here at Berkeley upstairs. And then we would repoint X-rays and, of course, radio too. So on paper, this looked like the simplest and clean and elegant experiment you can think of. And now let's see how the reality, what really happened that day. So again, we were waiting for 11 hours, just waiting for the sun to really go away. And we were using DECA. So our collaborator, Ryan Chornock, is a very expert optical astronomer, and he did not entirely trust all the machine learning algorithms and software that we have put together in the previous years. And so he started actually looking by eye at and doing differences between what was there before, what it was there later. And the challenge here is that every image is like the equivalent of, let's say, 68, I think it's 68 CCDs. So it's just like having 68 pictures at every single time that you have to try to find differences compared to what was there before. But the thing is that after 30 minutes, 37 minutes actually, we received this email where Ryan outperformed all the machine learning software of many hours and found the counterparts, and he sent that to the entire collaboration. So this is one of the we were one of the 6 teams that independently discovered the counterparts. So let's see what caused Ryan to send us that email. So here I selected already the galaxy that produced the merger. So what you're looking at there is one tiny portion of one of the 68 frames that Ryan was looking at every single time. So the game will be extremely easy here. So first of all, the big light that you have on the screen, that's a galaxy. That's a galaxy that is millions of light years away from us. And this was before the event. And now let me show you what happened later on. So as you can see, the 2 pointers are actually pointing you to the new source. Let me play again. This is where we were before. And after the merger, we had that new source. So this is the discovery of optical light coming from a neutron star merger that produced gravitational waves, the first and only so far. We have failed since then to find another one. But now the game becomes easy in the sense that I know extremely well where I have to repoint my best telescopes to study the source, and that's what exactly what we did. So we know where to repoint, and easy. So we use all telescopes we could put our fingers on, and we ask them, please, Lou, and have a look at the very same source, because I want to collect every single photon that is coming out of that source to understand the physics that is happening behind. So again, here is the artistic rendering of what happened, just to remind ourselves, is that we had those 2 neutron stars. They could not stay there. They were losing energy, and then they crashed. And that crashing is the source of the light that Ryan had detected. So the picture to keep in mind to better understand what I'm going to tell you later is that when the 2 neutron stars merge, they produce mostly 2 types of light. We have some fluffy region that is almost like a sphere, which is the one that produces a lot of optical and near-infrared radiation. This is the place where we're forging the heavy elements, so the gold that we are wearing. But then this event also had jets, relativistic jets, so something that is extremely collimated. And when I say collimated, I really mean it. It's just a few degrees opening angle. And this material travels at basically the speed of light, very, very, very close to the speed of light, Lorentz factor of 100. So this is the picture to keep in mind. So we have an event that has these 2 neutron stars produce something very spherical, and then some jets. The spherical part produce optical and near-infrared. The jets shine bright in X-ray and radio. So let's see what happened here. So we have the gravitational wave trigger, and as I told you, it took 12 hours before the night would fall in Chile, and that's the time it took to us to understand, for Ryan actually, to understand where the source was. Once we knew where the source was, then we repointed all of our telescopes. And just 1 hour, 1.7 hours after the localization, we were on target with a very large array in Socorro. This is absolutely groundbreaking that we could turn all the antennae in just 1.7 hours. So we got very excited, but again, we were expecting to see very bright radio emission from the jets. That's what I told you. This produces the most relativistic jets in nature. And we look at the image, and first of all, this is how a radio image might look like. The reason why the sources are so elongated is just a consequence of the deformation. So it's an instrumental effect. We got super excited about that source, but then we overlaid the optical position, and you can see that the yellow circle does not fall on top of the radio source. The radio source we got super excited about was not the neutron star merger at this point, but it was just the host galaxy. So galaxies can also produce radio emission. So no radio at the beginning. We were able 1.5 days after to get the first spectra of the in the optical of this event, and 2.4 days after, this is the time it took to get on target with a very powerful X-ray instrument like Chandra. There's a whole story behind the 2.4 days, but fundamentally there is some time that it takes to communicate to the spacecraft and sometimes to upload the command. But bottom line, it took 2.4 days to get there. And here is how an X-ray image of the same part of the sky looks like. And every little square right there is a photon. And if I tell you where our source is, that's a yellow circle. There is absolutely nothing there. So 2.4 days after, there are 2 photons. Those are photons from the background. Our source is not producing anything. But the people in the optical instead were having a ton of fun. And here I'm going to use an animation from, this is actually a simulation from Dan Kazan. Dan Kazan is also faculty here at Berkeley, and then was able to predict extremely well the light coming, the optical light, optical infrared light coming from this merger. So this is the fluffy thing I was referring to before. This is the place where we are forming the heavy elements. And as you can see, Dan was able to predict 2 pieces of a story. There is the blue part and the red part. Basically, there are parts of this neutron star ejecta that produce more heavy elements. Those are the red ones. And then there are others that produce less. If you look at the days since merger, you can see that my optical near-infrared colleagues were having a lot of fun in the first 2 weeks, and they were detecting a lot of signal, spectra, you name it. They had a lot of signal, but in the X-rays and radio, pretty much nothing. So looking at the spectra of this event, here I'm showing an infrared spectrum taken by Ryan. So you can see we have those big wiggles, and the black are data and the red are models by Dan Kazan. So here there is only one message, that the model and the data really go together well, exceptionally well. And I know that it might sound surprising, but trust me, predicting spectra from first principles for this kind of events is extremely challenging. And the fact that the data and theory go together so well without much tuning is absolutely amazing. The reason why they go so well together is because Dan Kazan assumed in his simulations that neutron star merger would produce the heavy elements I was telling you about. So then added to his simulations the key ingredient that all the orange colored elements would be produced in neutron star mergers, and that's what gives this very, very, very special shape of the spectra that Ryan was able to detect. So those wiggles are the reason why I can be here and tell you with high confidence that this neutron star event did produce the heavy elements. Now, the question that we have right now in the field is no longer if they produce heavy elements, it's more of how much of the heavy elements in the universe are produced by neutron star mergers. So while all of this was happening in the optical skies and near-infrared skies and UV skies, X-ray and radio astronomers were still empty-handed. And we were empty-handed for 2 weeks. This is the Chandra X-ray image at 15 days, and now I can place the circle just like before, and now you see a source. I know it might look pathetic. Those are 9 photons. Those are my favorite 9 photons in the universe. These are the first time I can say that these 9 photons are X-ray photons coming from a neutron star merger. So that's why they are so special. In general, X-ray astronomy is photon starved, and you don't build those beautiful pictures as the optical people. Same story for the radio. Finally, after a couple of weeks, the radio also come into view, and we start detecting a very beautiful signal. But as it always happens, when things start to go very well, something happens that is not ideal. And here, the not ideal part is that the sun starts to get too close to our source. So a lot of the instruments can't actually point too close to the sun. And so observations have to stop. This is true for X-ray instruments. It's true for optical instruments, UV instrument, infrared. But the beauty of radio is that that is not true for radio. So while everybody else had to stop observations, radio people, we could enjoy some fun while we could observe the development of this source. And here is a plot that shows you what happens in the X-rays and radio. So you'll have luminosity on the y-axis and time on the x-axis. And you can clearly see that this source took a while to reach peak in the X-rays and radio. So while things were already over after 10 days in the optical, X-ray and radio, the fun lasted longer, all the way to 100 days, and then it started to decay. I want to try in this next few minutes to give you an idea, a feeling for why this was happening. So again, our thinking is that the X-rays and radio, they come from these jets. Those are extremely powerful jets. So for the normal gamma ray bursts that we see, those that were discovered by the Vela spacecraft, for example, those are typically discovered with the jet pointing directly at us. Instead, in this case, for this neutron star merger, since we were not detecting this event through the gamma rays, but we were getting the trigger from the neutron star merger from the gravitational wave part of the sky, we were capable of detecting the event off axis. So we were not aligned with those jets, we were just a little bit off axis. And this is the key. So this is special relativity coming into play. So if I have a source that moves very, 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 very fast, then for me, observer, that I'm looking at that source that moves fast, I'm gonna see most of the light emitted by that object beamed along the direction of movement of that source. This is just a special relativity effect, not general relativity, special relativity. And so what that means is that if instead of being there as that girl at the telescope, I am instead here at the beginning, I don't see anything because my object is producing light in the wrong direction, if you want. And it's only after a while, once the source starts to decelerate, that relativistic beaming becomes less severe, and that allows the beam of light to intercept my line of sight. And that's when I start seeing photons. So basically, if I'm not aligned with the jet, I need to wait for that source to decelerate. And that's why we had to wait for the light from the jet, the X-rays, and the radio to actually peak. So this is the time it took for that source to decelerate. The cone of radiation would open up, and I am the observer, and I would see them. I know we are at the end of time, so I'm gonna try to summarize what we have learned. So as of August 2017, we have learned for sure that neutron stars mergers are one of the sites of heavy elements production in the universe, and that comes through that fluffy part that they never named, but it's named kilonova. And we also know now that those events produce these relativistic jets through that very long rise that we could sample of the X-rays and the radio. So after many years after the merger, so this is an image of 3.5 years after the merger in the X-rays and radio, a surprise happened where we were not expecting to find any X-rays whatsoever, and no radio. And if you look at the radio map and you look at the orange circle inside 17 there is nothing, and that was consistent with our expectation of the jet is now decelerated and there is nothing for us to see. However, if you look at the X-ray image on your left, you can see that my circle in orange is full. And that was not expected. That was a surprise. So in other words, years after the neutron star merger, we discovered the presence of more X-rays than we were expecting. And what we're trying now to understand is what is the origin of that component. The reason why this potential access might be exciting is because it might be related to the big question mark that I told you about at the beginning. It might be related to what we have formed. Did we form a black hole? Did we form a neutron star? That's why it's so exciting. So where are we going from now? So 2017 is now a few years ago, and let me just give you a feeling of what we're trying to do in the next years and trying to go from one source to many sources. So here at Berkeley, together with LBNL, Peter Nugent started putting together a new survey. It's called the La Silla-Smith Southern Survey, or LS4. And that's a survey that one of those surveys with big eyes that will allow us to pave the sky very, very quickly and trying to find counterparts more efficiently. In general, we have started few weeks ago, a new center here at Berkeley. It's a multi-messenger research Center for multi-messenger research on astrophysical transients and outreach. It's a multi-raptor center, where the idea is that all of us faculty that work in a multi-messenger research at Berkeley and in the Bay Area are coming together and trying to understand how to make the most of these new ways to study the sky. And I heard you had a lecture from Josh before me. Josh is one of the faculty affiliates of this center. And with this, I know I went maybe a little bit long. I just want to end. I really want to thank you for your attention, and hopefully I was able to make you excited about this new era of investigation in astrophysics. Thank you very much. I'm happy to take questions.